All right, so let's pick up where we left off. We were looking for the volume of a solid that I'm not going to attempt to sketch here because there's kind of too much going on in 3 space to really get a good picture of it, at least with my artistic skills. So we're going to just work with the set that we have here. One thing I do want to point out, though, the volume that we're looking for is not a simple matter of just going straight to a double integral at this point. Because, for example, if I wanted to take a double integral of just a single, a single function representing a surface, the volume it's going to give me is the volume between, the volume beneath that surface going to the xy plane. And the solid that we're talking about actually doesn't go down that far. The volume is trapped between 2 planes in this parabolic cylinder. So the way we're going to think about it, let's go back to this. Remember, this is the YZ plane, and these 2 lines are actually the traces of 2 planes in the YZ plane. So this little pocket that I described here would carve out a piece of this parabolic cylinder around here somewhere. And if you notice, one of these planes, as far as this little pocket is concerned, is above one of the other plane. So if I were to find the volume underneath this plane right here, over this region D, and then find the volume as a separate problem, find the volume underneath this plane over this region D, I could take the larger volume and subtract the smaller volume and be left with the volume of that little solid that I'm looking for. So we're actually subtracting 2 different volumes here. So to see what that would look like, first of all, notice that the plane that lies, the plane that's higher between these 2 is the plane z equals 2 plus y. So that means the first volume that I want is going to integrate over d, but it's going to be integrating the function 2 plus y dA. And then I need to subtract from that the volume that I would get under the plane that's closer to the xc plane. And that volume would be given by this double integral right here. Use my other function, 3y dA. And here's where those properties come in really handy, because I could evaluate this as 2 separate double integrals, but because I'm integrating over the same region in both cases, I can just combine these into a single integral and subtract the integrands. 2 plus y minus 3y is just 2 minus 2y dA. So even though we have to think of it as a difference between 2 volumes, properties of integrals let me consolidate these into just one integral, and then this is going to be pretty easy to solve. So this is the point where we want to go back to how we defined this set D up here to create an iterated integral that we can solve. And again, we were looking at a type 1 region here, so x is going to go from -1 to 1, and y is going to go from x squared to 1. We're integrating this function right here, 2 minus 2y dy dx this time. Okay. So this is pretty easy to integrate. I'm just going to get, I could factor a 2 out. I'm not even really going to bother with that here, though. It's just going to give me 2 integrated with respect to y here, so it's going to be 2y minus y squared, and we evaluate that from x squared to 1. There's my dx right there. Substitute the x squared in there, integral from -1 to 1 of, or actually, sorry, substitute the 1, and then that's going to give me, let's see, so these are y values. 2 times 1 minus 1 squared would just be 1. Minus, and then if I were to substitute the x squared, that's going to become 2x squared right there. X squared squared, that's x to the 4th. I'm subtracting something that's already negative, so that's going to become plus x to the 4th dx. And then again, this is just integrating a polynomial, which is easy to do. I don't need to work that out for you, but I will point one thing out. This polynomial is an, oops, move that up a little bit. This polynomial is an even function, and it's being integrated over an interval that's symmetric about 0. We've encountered these before. You talk about these in Calculus 1 and Calculus 2. There is a shortcut for integrating that. I'm not going to show it to you here, but if you're doing this by hand and you're filling in the gaps that I'm leaving, use that technique. It makes this easier. This should come out to 16/15 once you've done all the work there. Okay, so that's evaluating. Well, that's finding this volume that we were discussing here. So I have one more example I want to do in this section, and it's going to use property 6 here. Remember property 6, which puts bounds on a double integral if we can put bounds on the original function, the integrand, and if we know the area of the region that we're integrating over. Okay, so we're going to use this property in an example. So it says approximate the double integral over the region t of this function, sine to the fourth of x plus y dA, where t is the triangular region enclosed by the lines y equals 0, y equals 2x, and x equals 1. Okay, if you tried to evaluate this directly, you're going to find that because of the integrand that we're using, you're going to hit a wall pretty quick. It's not going to come out nice. In fact, it may even be something that's impossible to integrate directly, or if it is, it's going to require a lot of kind of clever techniques. So we're not looking for an exact answer here. We just want to approximate. And the key to using that property we just talked about is to figure out what the bounds on the integrand are. So starting with sine to the fourth of x plus y, it doesn't really matter what x and y are. I know that sine is bounded by -1 and +1. But then if I go and raise it to the power of 4, this can only come out non-negative. So really, this, no matter what x and y are equal to, this is going to come out to some number between 0 and 1. We know this for sure. Okay, so that 0 is like the little m, and that 1 is like the big M in that property 6 on the previous page. So the next thing we need to do, if we're going to use that property, we need to know the area of the region that we're integrating over. So I'm going to sketch this out and see if I can come up with its area. It's the triangular region enclosed by the lines y equals 0, y equals 2x, x equals 1. That's easy to draw. So y equals 0, that's the x-axis. X equals 1 is a vertical line passing through 1, so this. And then y equals 2x is a line passing through the origin with a slope of 2, so that's y equals 2x. That was x equals 1 right there. Okay. If I plug this 1 into this function, I would see that this takes me up to 2 here. So this triangular region T has a base of 1 and a height of 2. That means the area of that triangular region is 1/2 base times height, 1/2 times 1 times 2, which is equal to 1. Okay? So how do we then use the property to get an approximation? Well, the integral of this function over t, sine to the fourth, x plus y dA, we can put bounds on it. Remember, it's going to be little m times this area over here, and big M times this area over here. Well, 0 times 1 is 0. 1 times 1 is 1. And so we get that the integral of this function over our triangular region is going to come out to some number between 0 and 1.